This is Team Purple 7 bringing the Physics Project 2 to you. My name is Lily. We also have Charlie and Jackson here with us today. Our problem that we chose was the boxes problem. So as it reads, two boxes, one with one mass, we recognize that as MB, and the other red box with MR are sitting on a level horizontal frictionless table. On the right edge of the table, the blue box is in contact with a spring. This is the constant K that has been compressed by a distance of xi. Starting from rest, the blue box begins to move to the left across the frictionless surface until it collides with the red box. The box is now stuck together, slide toward the left edge of the table where they encounter a spring identical to the one on the other side of the table. Our problem is to determine the maximum distance that the second spring does compress, and so we're going to go over that throughout the presentation today. So we used all of our understanding and plan. That's what I'm going to go through, and then Charlie's going to go over our calculate part, and then Jackson will finish up with our sense making. But we look at all three of these sections, and we're going to get into understanding and planning. So we recognize that there are three interactions within this one problem. So we have the spring 1 and the blue box and the red box, and then the blue box, red box, and spring 2. And all of those are in the outlined boxes there. So that first interaction is going to be in blue, second interaction is in red, and then that third interaction is in the purple box there. So we kind of deconstructed the diagram to better understand it and what we know. So we do know that the spring 1 was compressed, and we know its initial position. We know that spring 2 was compressed as well, but we are solving for the final compression. We do know the mass of the blue box, and we do know the mass of the red box. So, and then it also says that we need to solve for the unknown, which is the compression of spring 2, which is going to be that final distance. So the assumptions that we can make upon this is that both springs are idle, which means they are frictionless, massless, and linear. The surface is also frictionless. This is explicitly stated in the problem statement. Also, air resistance is negligible, and the boxes do not deform upon colliding. So we can represent this physically. So here's a diagram of what we do know. We know the initial position of spring 1 and that final position of spring 2, with the blue box moving towards the red box, and then those two arrows showing that they move together once they collide. And so we drew an energy bar graph for that first interaction. So that's solely within the spring and the blue box. So we do know with the initial position of that spring, we know that there's a lot of potential energy because it's already compressed. And then we know that the kinetic energy is really low. And then once that box moves away from it, and we know that the kinetic energy does increase and that potential energy does decrease. So when those two boxes collide, that is known an energy bar graph. That's a momentum vector diagram. And so we drew a momentum vector diagram for that one. So below you see that the momentum of the blue box is initially going to the right, and the momentum of the red box is stationary because it hasn't been hit yet, so that right before that interaction. So we know the momentum is going to the right. We know that after they interact, the blue box is moved slightly to its momentum vector is slightly to the left, while the red is slightly to the left, and so we do know that that is stationary because they stick together. And then afterwards, they both are going to the right direction, so the momentum again is to the right as they go into that third interaction, which we are looking at right here. So we can see that this interaction is between both the blue and the red box, and then spring 2. So initially the spring is not being compressed, so its kinetic energy is really high while the potential is really low. And then when the blue and the red box come in contact with the spring and compress the spring, we know that the potential energy does increase and the kinetic energy does decrease.
Alright, so now we are moving on to calculations. Like we previously said, the problem can be represented by three separate interactions. The first interaction is with spring 1 and the blue box. We know that the net work, which is the integral of the net force times the change in distance on the system, is 0 because the spring does not move from its anchored point. From the work energy theorem, this means that the energy is conserved, so the change in energy is 0. We also know that spring 1 has spring potential energy, known as U spring, that changes while the blue box has kinetic energy, represented as Ke. This interaction can be more accurately displayed with equations. Initially, spring 1 is fully compressed, so it has max spring potential energy, which is given as 1/2 times K times xi squared, where K is the spring constant and xi is the length compressed. The blue box initially is at rest. However, after spring 1 fully extends, it now has no spring potential energy. The blue box now has been hit and is now moving, so it has kinetic energy, which is 1/2 times mb times vb squared, where mb is the mass of the blue box and vb is its velocity. The change in energy is zero and shown as ui plus kei equals uf plus kef. If we substitute in the equations, we get 1/2 times k times xi squared equals 1/2 times kb times vb squared. Now we can move on to the second interaction, which is the collision between the blue and red boxes. We know that the collision is perfectly inelastic because the boxes stick together, so the change in kinetic energy is not zero. It should go down. However, we can solve the problem with momentum. Since there is no important external force on the system, we get that the net impulse, which is the integral of force times change in time, is zero. With the impulse momentum theorem, the change in momentum must also be zero. Both boxes also have their respective momentums. We can also model interaction 2 with equations. Initially, the blue box is moving and has momentum of PBI equals mb times vb, where mb is the mass of the blue box and vb is its velocity. The red box is at rest, so its velocity is zero, meaning it does not have momentum. However, after the collision, the two boxes are now moving together. This means they have the same velocity, which is shown as vr. The only difference could be their masses, so the final momentum of the blue box is mb times vr, and the momentum of the red box is mr times vr, where mr is its mass. Since the change of momentum is zero, pi equals pf. This gives mb times vb equals mb plus mr, together times vb. The final interaction is between the blue box plus the red box and spring 2. Like from the first interaction, the network is zero because the spring does not move from its anchor point. This means that the change in energy is also zero. The blue box plus the red box has kinetic energy, and the spring 2 has spring potential energy. We can also model this interaction with equations. Initially, the blue box plus the red box are moving, so they have the combined kinetic energy of 1/2 times mb plus mr together times vr squared. Spring 2 is originally at equilibrium, so it has zero spring potential energy. However, the blue box plus red box eventually hits the spring. This causes them to stop moving, making their kinetic energy zero. However, spring 2 is now compressed, so its spring potential energy is 1/2 times k times xf squared, where xf is the length compressed. This is also what we're solving for. Since the change in energy is zero, ui plus kei equals uf plus kef, which gives 1/2 times mb plus mr together times vr squared equals 1/2 times k times xf squared. From the previous few slides, we can summarize each of the equations from the three interactions. In the first interaction, we know the change in energy is zero, giving us 1/2 times k times xi squared equals 1/2 times mb times vb squared. From the second interaction, the change in momentum is zero, which results in mv plus times vb equals mb plus mr together times vb. Finally, in the third interaction, the change in energy is again zero, giving 1/2 times mb plus mr together times vr squared equals 1/2 times k times xf squared. These three sets of equations share certain variables, allowing us to solve for xf. Between interactions 1 and interaction 2, we see that they share the common variable of vb, which is the velocity of the blue box. The final velocity of the blue box in the first interaction is the initial velocity of the blue box in the second interaction. Therefore, we can solve for vb for the first interaction and plug that into the second interaction, giving us the equation on the bottom right corner. Interactions 2 and 3 also share a common variable, which is vr. Vr is the velocity of the blue box plus the red box as they are stuck and moving together. The final velocity of the two boxes in the interaction is also their initial velocity in interaction 3. Vr can be solved for in interaction 2, which will be plugged into interaction 3, giving us the equation on the bottom right corner. From the previous slide, the final equation from the third interaction can be solved for xf. After simplifying the equation and canceling out terms, we get that xf equals the square root of mb times the xi squared, all divided by mb plus mr. We now have xf in terms of the originally given variables in the problem. After obtaining our expression for xf, we can plug in some realistic numbers. mb of the blue box can be 1 kilogram, which is like the mass of a slightly loaded cardboard box. mr of the red box can also be 1 kilogram. xi, which is the initial compression of spring 1, can be 0.20 meters. This can be a typical spring, such as a weakened suspension spring. If we plug these values in, we obtain that the compression of spring 2 will be 0.14 meters. In the following slides, we'll make sense of these answers.
So now we're moving into the sense-making portion of our problem-solving process here in these next couple of slides. So the first thing that we did here is we did a unit check to make sure our units checked out on both sides of our equation at the end. So we see here that on the left, xf has units of meters, and then on the right, the kilograms are going to cancel out in the numerator and the denominator, and leave us with just meters squared, the square root of meters squared, which will cancel out to equal meters, and that gives us meters on both sides of the equation. And this makes sense since we know we're solving for the compression of the second spring, which should be a distance given in meters. The next sense-making step that we took to check our answer was looking back at where we plugged in real values a couple of slides ago. And we know, thinking about this problem logistically, that the second spring should have less compression than the first spring, and the value that we chose for the first spring's compression was 1/5 of a meter, or 0.2 as we have written here. So we know that the answer should be less than 0.2 meters, and that is in fact what we saw when we plugged in real values, and we got about 0.14 meters. So this also makes sense. Okay, and the next thing that we did in the process is now make sense of our symbolic answer. And we can see that we did two things here. So the first thing that we did is a special case analysis in which the value mr is going to be equal to 0. So again, think about this problem logistically. In this case, because we have a frictionless surface, if there's no mass of that second object, we should get the same compression in the initial spring and the final spring. So it should be xi is equal to xf. And when we plug in mr is equal to 0, we see exactly that. We see xf is equal to xi. So this is a really good sign that it makes sense in that special case analysis. The second thing that we did here is another special case where we see mr is very, very large. So if the mass is 0 or if the mass is really large. And if we think about what should be happening in that case, we should be seeing less and less compression in xf with a greater mass. And that is in fact, again, what we see here because mr is only on the denominator. So as mr gets very large, our xf value is going to decrease over time. Or not over time, but decrease. Okay, so the final portion of our presentation is going to be reflecting a little bit on the problem-solving process and how we thought this project went. So we saw that in this problem, we used a lot of the concepts from both the momentum and energy units of the class, and a lot of the information that we covered both in the studios and on the homeworks and things like that were extremely useful. And then on the next slide, we'll go a little bit more specific into what exactly we saw in similarities between. So some very specific examples of problems that we saw earlier in the class that really helped us to solve this homework in particular was on homework 8, we dove into this relationship of potential energy and kinetic energy, initial and final, as you see written here in the homework 8 section. And then in homework 9, we talked about momentum and the relationship between the initial momentum and the final momentum. And for this problem, we found it really important to take both of these concepts and combine them. And that's what allowed us to solve this problem in the way that we did. So we found that those problems on those two homeworks were the most helpful in seeing us be able to complete this project and do it well. That's the end of our presentation. Thank you.